All right, I want to try to keep the momentum going here. Let's just kind of pick up where we left off. We have an example of related rate problem. And the problem actually used what we will consider to be like a strategy. Now, look, I'm going to show you this for a couple reasons, because it's true. Whether you decide to write it down or not, it's kind of up to you. You can write it if you want. It is in the book. I just really like to show it because you realize, oh my gosh, I do have to kind of think through these steps. The problem I did with you is a little simpler, but these steps will be helpful as we get into some more involved problems. There might be a diagram. There'll be this idea of interpreting. That's a big one. Okay, this idea of interpreting. Also, just identifying what you have to find. Now, that's kind of basic stuff when it comes like a word problem. Usually that's what you do. But the reason that step 2 and step 3 are just so important is because they have to do with these rates. And the main thing is for me to help you guys realize, oh my gosh, this is a rate, but this is not a rate, and just how to interpret the information. The idea of an equation that relates to variables. That was our volume equation. And nobody really blamed because I just told you, but there's going to become some problems. You have to figure out the equation. I'll show you how to do that. Differentiate with respect to time, and then evaluate and solve. Okay. Most of this is going to become kind of natural. That's the goal, obviously, but sometimes it's a little unnatural until we get to that spot, so we have to kind of think about some of these steps. I'll leave this up here now for the rest of the lesson, and what I want to do is start working through some of the examples. So take a look at the first one there. It talks about the water level dropping. Okay, now once you get good at these, you're not going to need a diagram for this problem. I'm still going to kind of draw the diagram just so that we realize, okay, this is what's going on. So we have some kind of can. I mean, maybe it's a soda can. There must be some type of hole in the bottom or something, because water is draining out of it, or some type of, water is draining out. Okay, so there's a water level. There's a water level, but that water level is dropping because, again, the water is coming out. Something's coming out of the bottom. And then we have some information here about the radius, which not a big surprise here that you can talk about the radius of an object like this. Okay, again, the diagram is really just so you get an idea, because I didn't bring in a can with a hole in the bottom. But the water is draining out and the water level is dropping. Okay, I won't ask this every time, but does it make sense for the water level to be dropping at the same rate that it's falling out? Maybe it does. Maybe you're like, geez, if the water is coming out of this, shouldn't the level be the same? But just think about it. The water level is based on many things. It's based on like the size in here. The drain rate is just based on, well, I guess just one thing, how much milliliters per second is coming out. Okay, they're related, but they're not the same. Now, step 2 and step 3, they're some of the key steps to start to interpret this information. Okay, one of the main things that we want to interpret, and I'm even going to label this as step 2, is that the 30 mils per second is a rate. And you right now need to think about what rate is 30 mils per second. D what dt? D what dt? Okay, now maybe you're like, I don't know. I'm not really sure. What do you mean? Well, what's changing? What's 30 mils per second? Like what, I'll dare to say, even like common measurement is changing. You're right. 30 milliliters. Milliliters is a volume amount. I'm changing by so much volume. Now, notice I didn't say volume equals 30. That's really important. Volume doesn't equal 30. The change in the volume over the change in time equals 30. We just called that a rate. Now, we kind of had to, I don't want to say pull that out of thin air, but we had to think, okay? It wasn't like given to you. Aaron had to kind of think, okay, that's the change in the volume. Now, here's something that I don't know if I would expect you guys to have thought about. I didn't even write it on the board correctly. That is that it's actually not equal to 30. What? It's not equal to 30. It's equal to negative 30. Okay, we have the idea of a negative rate. Now, especially if you've been in physics, that doesn't shock you, but when something is going down, it's a negative rate, and we're going to follow that same idea. You might want to highlight that in some manner, shape, or form. Again, if this is a negative rate, again, because we're losing it or it's going down. Okay, that's pretty important. Like that becomes part of helping us with our final answer. 30. Listen, I'm still kind of on step 2. Step 2 is just to like organize the data. And 5 seems to be another number that I need to organize. But listen, it's not a rate because it's not changing. The radius of this can is always 5. It's actually pretty simple. Just say r equals 5. And if you'd like, you can say r equals 5 centimeters. But the key here is that it's not a rate, but it's important. It needs to be identified. Technically, step 3 is to identify what you want to find. Back in the old days, it was just, I want to find out how many apples are in the basket. One of those word problems. Now I'm trying to find, you see the first couple words? How fast the water level. You have to read that as a rate. You have to read that as the change in something. The change in blank. D something dt. Now here's where some knowledge about the problem can help. I did draw the problem, but yet told you that it's not really necessary. The next problem we do, you'll see why it's necessary. But it's a can. You got to think about the dimensions of a can. You got to think about what the water level would really be in this problem. And I'm thinking of a word that starts with a...
Rate?
Well, it is a rate. We just have to figure out what type of rate. It starts with a H for height. Okay, it's the change in the height is really what we're trying to find in this problem. We're trying to find the change in the height over the change in time. It's a height rate. Water level is a height rate. I hope you guys know that the problems I'm going over are ultimately to allow you to do some problems on your own. So we're doing a problem with a can. I'm sure that sometime down the road you're going to see a problem with a can and you'll be able to use some of these same ideas. Okay? Do you understand that everything I did right here, I know it took a little time, but everything we did was to kind of organize the information so that we can start to think about technically step 4, which is an equation. An equation. Now, these equations don't just come out of thin air, but they do have to connect the stuff that's up here. What's up here? H's, R's, and V's. So we have a can, and we have H's, R's, and V's. The formula that relates these letters is the formula for the volume of a can. Pi r squared H. Don't worry about if you didn't have that formula memorized from geometry, but do think about that formula uses the 3 variables. Yes, we're in kind of an interesting time. You guys will find out that we can do problems that involve more variables, more than just 2. Okay? Now, before I do the derivative, there's a little pre-step. And the pre-step is that anything in this given that is constant, anything in this given that is constant can be plugged in pre-derivative. Okay? Because it's not going to change. In other words, the derivative of this is just 0. So I don't need to do the derivative of r. You'll catch on to more of that as we keep going, but I don't need to do the derivative of r because it's not a rate. It's not going to change. So I can just plug it in as a constant. It technically wipes out one of the variables. So we have volume equals 25 pi times h. Volume equals 25 pi times h. Okay, now for the fun part. The derivative with respect to time. Basically the whole essence of this lesson. Now the derivative with respect to time, I guess it's technically another step up there. When you do these problems for an assignment or on a test or quiz, you don't need to have all step this, step that, but I'm just trying to kind of organize it because we're now ready to do the derivative of v with respect to time, which turns this into a rate formula. Now the derivative of 25 pi h, interesting, 25 pi h. 25 pi is just a coefficient. That's the second time you've heard that. But I want you to notice that the variable that I'm going to do the derivative for is not raised to a power other than 1. This one was raised to a higher power, but the variable I'm going to do the derivative of is only raised to a power of 1. So what's the derivative of h? Okay, it's not 1. It's not 1. It's not h. It's actually just dh dt. When the variable is to the first power, the derivative is just going to be the derivative. I pointed over here, though, because I want you to start to see how this one was different. It was to a higher power. And that's why I had to do the chain rule. All right, that's your formula. It relates the rates. And it also has what I'm trying to find. It has dh dt. It also has what I'm given. And so it's plug-in time. You just plug in. It's actually kind of simple algebra. Just plug in negative 30. And I'm sure you're going to divide by 25 pi. Again, kind of the easy step, but notice that the answer, well, it's supposed to make sense. For one thing, the answer is negative. That's because my height is decreasing. Secondly, there's an interesting phenomenon with the labels. What am I talking about here? Well, the numerator was in technically centimeters cubed per second. Centimeters cubed is volume. So we had centimeters cubed per second, and we divided by 25 pi. Help me out here. This answer is supposed to be coming out to be just linear. Well, I guess 5 squared technically was like centimeters squared. And so it's not a big deal, but I do want to point out that the labels actually cancel to make sense. Again, I get centimeters squared when I plug it in. So my cube and my square give me just a linear measurement. And height, the change in the height is indeed linear. Hmm. I'll tell you what. I kind of know what we need to do and how much time we have, and it probably would make more sense to not have that get split up or hurry up and do it here on a Friday. So we'll do the hot air balloon problem next time. Okay. Maybe there's something that you need to do over break. It depends, I guess, on if you finish the last assignment, right? Assignment 4.5, linearization and differentials. Make sure that that is something you're ready to turn in on Wednesday.